My name is Elise Bailly, and I'm a PhD student at the Laboratoire Charles Fabry, and I'm supervised by Jean-Jacques Greffet and Benjamin Vest. So in my talk, I will speak about the spatial coherence of light emitted by thermalized ensembles of emitters coupled surface waves. To better understand why it's interesting to study such a thing, let's first take a first look at what is the spatial coherence. So consider you have an ensemble of emitters. It can be atoms, quantum dots, dye-molecules, whatever you want. Each of them emits light. So the key point here is the fact that the emission of light is intrinsically a random process, so that the resulting field would itself be a random variable. And it's important because then it's possible to define the correlation function of this random variable at two distant positions, R1 and R2, and actually knowing about the spatial coherence is nothing more than wanting to know whether the fields are correlated at two distant positions. So let's imagine you have an ensemble of independent emitters. In that case, the resulting light would be incoherent. Each emitters will emit light in random directions with random phases. So you will obtain light in every single direction of space, or almost. You will find light everywhere. On the contrary, if for some reason the light is coherent, then the field would interfere constructively or destructively in some positions of space. And this is interesting because you can think of spatial coherence to design, for instance, directive sources. You would obtain light only where the fields interfere constructively. And how can we how can we know that the fields are correlated? For instance, you can do interference experiments with Young's double slits. So what you do, if you want to know whether these two fields are correlated, you isolate these fields and you observe the fringes pattern on the screen. So for instance, let's imagine you want to know, you have the hypothetical case where your source is a point source, it's monochromatic. In that case, the fields at these two positions are perfectly correlated. And as a consequence, on the screen, you would observe perfect fringes, perfectly visible. And it's important to note that the visibility on the screen is directly proportional to the modulus of the correlation function at these two positions. But what happens now if you add another sources, which is completely independent from the second one? On the screen, you would observe a decrease of the visibility because each source will generate its own pattern fringes. And so it leads to a drop of visibility and thus a drop of correlation at these two positions. And then there I just put two sources, but you can imagine that if you have, well, not an infinity, but many of them, you will lose on correlation at these two positions. And it's important to say that because I will come back to this experiment after, that experiments have indeed been done with dye molecules deposited on silver, and they did realize these interference experiments with Young double slits. And what is surprising is that they observed fringes on the screen. And from what I just said before, it's surprising because since it's an ensemble of independent emitters, we shouldn't observe any coherence. So in my talk, I will explain you how we can quantify the spatial coherence and then how we can use it to understand the physical origin of spatial coherence in such a system. So the first question is, how can we compute the spatial coherence? So as I said, the spatial coherence is nothing more than the field correlation at two distant positions. So let's assume you have an ensemble of emitters. You want to calculate the field correlation above this surface. The first thing is the fact that you can express the correlation of the fields thanks to the cross-spectral density tensor W. Secondly, when you have an ensemble of fluctuating sources, the fields generated by these sources can be expressed thanks to the green tensor. So this expression is a general and linear expression of the fields. So you see that if you want to compute the correlation of the fields, you just have to know the correlation of the current sources. And it happens that we do have an expression of the current sources, of the correlation of the sources, thanks to the fluctuation dissipation theorem. And this theorem is quite interesting because it connects the fluctuation of the current densities to the left part of the equation, which is described by the statistical physics, to the dissipation with the imaginary part of the dielectric permittivity, and which is given very deterministically. So at the end, you have an expression of the field correlation thanks to the dissipation. And it's interesting because actually what we would do at the end is to compute the absorption to obtain the field correlation. So we will come back to this later, but what you do is to put two coherent dipoles of unit amplitude at these two positions, R1 and R2, and you can compute the absorbed power integrated over the layer of emitters for each cases. And you can also do it when you put the two sources at the same time, and you obtain the total absorbed power. So if the sources were in coherence, then the absorbed power in the layer would only be equal to the sum of the absorption generated by each source separately. However, as I said, the sources are coherent. So they will generate an interference pattern in the layer of emitters, and we have to take it into account by adding a complex term, which is, well, sometimes called as the mixed losses, but this is not very important how we call it. What is important is to understand that we have to take into account the interference effect. So a general relation connecting the absorption to the correlation has been derived in the following article. I said it's on arXiv, but it has also been accepted in Optics Express. And it connects the cross-spectral density tensor W to the mixed losses. So this calculation is based on macroscopic fluctuational electrodynamics and the fluctuation dissipation theorem I showed you before. And you can note that this relation is valid only if you can define a temperature and a photon chemical potential for the populations of carriers involved in the light emission. So we can show a first very quick example to know how we can use this expression. So let's consider you have, a silicon carbide Hawk space, and you illuminate it by two horizontal current sources. And what you can do is to plot the modulus and the phase of the mixed losses, which will give you all the information you want on the cross-spectral density tensor. And the magnitude of the losses would be, corresponds to the strength of the interference-related effects, while its phase corresponds to the dephasing between the two sources, for which the magnitude will be either maximum or minimum. I won't spend too much time on this graph, but what is important and what I want to show is the fact that the losses are phase dependent. And another way to show it is to plot the losses per unit volume in this layer. When you put the two sources, you separate the sources by a distance of lambda over 2, and either you put them in phase or in a position of phase. And you see that when you integrate the losses over the volume of your silicon carbide space, you obtain an absorption which can be 3 times higher, just depending on the phase. So this is quite visual in here. So now that we have means and a way to compute the correlation, we can go back to the experiment I showed you before to see how we can use it to understand the spatial coherence. So I remind you the experiments. So Young's double slits have been put just above a layer of dye molecules. So these dye molecules were deposited either on glass or on silver. And the striking fact is the fact that you observe fringes when the dye molecules were deposited on the silver layer. So as I said, it's surprising because we don't expect any spatial coherence for an ensemble of independent sources. And it raises the question of the mechanism which leads to a long-range correlation. So to analyze it, to address this issue, it's possible to show that the system is thermalized so that we can use the general relation I showed you before. And in the specific case where the sources are at the same height and the system is infinite, you can rewrite the general relation into this very simple formula. And this is the one we will use in the following to understand the physical origin of the spatial coherence. So here is the system we consider, and which is exactly the same as the one I showed you in the experiment. And to better understand the modes of the system, the first thing we do is to plot the reflectivity as a function of the energy and the parallel wave vector by sending a plane wave from the top in the glass. So from this graph, we can say at least two things. First, that the modes are plasmonics. Secondly, that there exists a strong coupling between the dye molecules and the surface plasmons with the opening of a gap around 2 electron volts, and it leads to the formation of excitant polaritons. To better understand the role of this coupling regime in the existence of spatial coherence, we will plot the normalized correlation function around the strong coupling zone, so around 2.07 electron volts, and far away from it. So let's start at 1.6 electron volts. Here is the normalized correlation function. So as a function of the position of the distance between R1 and R2, and in red the envelope of the curve. So this is only the interpolation of the maxima, and in the following I will only show this red curve is the envelopes of the curves. So in that case, you observe a long-range correlation. And I don't know if you remember, but in the interference experiments, what we observed was fringes only when the dyes were deposited on the silver layer. So it's what we can check here, what happens if we remove the metal layer. So this is the blue curve we obtain, and you can see a clear drop of correlation. So this is consistent with the experiment. And what happens if we compare it to the correlation at 2.07 electron volts in the gap? So here is the correlation function, and you can see that the correlation also drops, whereas there is still the silver layer for both cases. And the explanation is that in the gap, it's not possible to excite any surface waves. So we can deduce that the surface waves are responsible for the spatial coherence. And the reason why, well, we can do a very simple schematic diagram to understand why the surface waves are responsible for the spatial coherence, is the fact that when the surface waves propagate, they will contribute to the field at position R1, but also at the field at position R2, so that these fields become correlated. So as a conclusion, we can say that we could compute the correlation thanks to an absorption coherence relation. And with the analysis of the mode structure, it was possible to deduce that the spatial coherence was due to the propagation of surface plasmons in a very specific system consisting on dye molecules deposited on silver. And I also would like to add that it could be a convenient tool to design directive sources based on spatial coherence and ensembles of thermalized emitters. I thank you for your attention, and I'm willing to answer your question if you have any.